Recording is rolling. It is Monday, April 21st. So we're going to do theory of relativity this week. Before we get into that, did you guys see this science story from the last few days that scientists might possibly have discovered life on another planet? You guys see it? Yeah, right. So, in case you haven't, tell you the story. If you haven't, if you have seen the story, then you probably read the same articles as I have. But it goes about like this. So there's a telescope that was set up a few years ago. Do you guys know this one, James Webb Space Telescope? Okay, so it's one of the most powerful telescopes we got right now. Right now, it's orbiting the L2 point, I think, around the moon, something like that. Okay, but uh, one thing that it's looking at is exoplanets. Now, how do we know that there are exoplanets? See, that was an open question just a few decades ago too. It's like how prevalent are planets around stars? Do just a few stars have planets? Do lots of stars have planets? Okay. And we found out in the meantime that yeah, actually, lots of stars have planets, so like proportionally. Okay. And here's how we know that there are exoplanets because every time a planet passes between its parent star and Earth. But now this star, this is not the scale at all. This might be like many, many, many light years out, right? But every time a planet passes in front of it, the light from that star, well, not as much light reaches us. The light dims a little bit. And if you know how much the light dims, and you know how much time it dims for, you can put those two facts together and get a pretty good idea of how large a planet would be that's passing in front of it, and also how far away that planet is from its parent star. And one of these planets, we're looking at exoplanet around so some star out there. If you want to Google it, it's K2-18b. Looks about they said about 2.5 times the size of Earth. Now I think they're referring to diameter, which would be a different question in terms of volume and gravity, but so that's okay. And also, it looks like it's in what's called the habitable zone. So if it was too close, then it would be too hot to like Mercury or Venus. If it was too far away, like Mars or beyond, then it'd be too cold. If it had water, then the water would be frozen over. So, right? But Earth is in this habitable zone, this Goldilocks zone, where water can be liquid. And as far as we know, it seems like you have to have liquid water to support life. Is there something exception to that out there? Who knows? The universe is big, but as far as we know, it seems big. Right? So this particular planet looks like it's in the right place, blah, 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 right? But a lot of planets are, right? But what's also special about this planet, what's new, is that, see, you can determine what chemicals are in its atmosphere by spectrometry. So here's some starlight that passes through the atmosphere of this exoplanet scan, like way, way out there somewhere, okay? And you can use spectrometers here on Earth from this data from James Webb Space Telescope to determine chemical composition. And one of the chemicals that was found is this one right here. It's called dimethyl sulfide. Now, as far as we know, the only way to create dimethyl sulfide is through organic processes, through life. So right now, there's a couple of questions going on. One is that, are we really seeing what we think we're seeing? Is this actually dimethyl sulfide, or is it some fluke and like, oops, we thought we were seeing it or not, right? So that's a question. Another question is, if this really is dimethyl sulfide, then is there a way to create this chemical compound in these significant quantities that's not through life? Right? Because if not, then there's a good chance that this planet might be covered in life. Right? Now, would that life be intelligent, or would it be like really basic? Would it be even complex? Would it be just, is the planet covered in oceans that are covered in algae types? Right? Who knows? Those are all open questions. But yeah, right now it could be exciting news, and well, 50 years from now, we'll look back on this year, and it'll either be significant or not. So we don't know. So some open questions, but okay, so that was the story we're sharing. All right, so anyway, let's get back to this relativity this week. Relativity. So got some concepts for you guys, got some posters, got a couple of video demos. We're gonna hit all that today. Now, you guys have some paper out? You guys got some paper? All right, so first, we're going to start with the basic Newtonian relativity question. Now, when people say relativity or theory of relativity, they're normally not talking about Newtonian relativity, but I think that's a good starting point anyway for this whole story we're going to kick off. So here we go. We got Alan and Bob, and they're in these paddle boats. Let's say they've been racing back and forth on this lake all day, and they keep tying. So they say, let's start at the start-finish line on the left side. We'll race all the way down to this tree on the far end of the lake and then back. Okay. Let's say turnaround time is negligible, so don't worry about that so much. Okay, but they can each paddle at 10 meters per second, so they keep tying over and over and over. Okay, then finally one day, or one part of the day, Bob says, "Hey, look, there's a river right over there. It has a river current going downstream at 2 meters per second. Ooh, right? Let's rerun this race." Except Bob's now going to be in the river. So they both start at this end at the start finish line, but now Alan's in the lake, Bob's in the river. They're each going to go to this tree at the far end and then turn around and paddle back towards that start finish line. Okay? Okay. So remember, they can each paddle 10 meters per second relative to the water. Okay? Alan's in the lake, and so the water is not moving relative to the tree. Bob's in the river that's moving downstream at 2 meters per second. So he's getting a boost from the stream one way, but then he has to fight the current the other way. Okay? Question is, who wins the race this time? Oh, one more number I throw at you guys. I gave you guys a distance of 120 meters. So go ahead. Take a minute, solve that on paper. See who's going to win that race. Who wins the race? They got paper. Make sure everybody's got paper here. Oh yeah, everybody's got paper. All right, nice. Solve it. Who wins that race? If you know what you're doing, go ahead. If you need a hint, or you guys tell me, guys, what formula? It's a real short formula. What's the formula you need to solve that? Huh? Distance equals speed times time. Yeah, yeah. You guys ever drive on the interstate? See a billboard says Jacksonville is 180 miles away. Say I'm going 60 miles an hour according to my speedometer. And then you do a quick calculation. It takes you what, 3 hours to traverse that distance? Right? Distance equals speed times time. Okay. In fact, if you want to see who wins a race, and they're both going the same distance, then what variable should you be solving for to determine who wins the race? Time. Does it make sense? Whoever completes that distance in the shorter time wins the race. Okay, so keep going. Yeah, there and back. Yeah. So going from the start finish line all the way down to the tree, and then all the way back to where they started. So two-way trip. I'm going to say show of hands here real soon. If you did calculation, you're going to get it right. Yeah. Okay, yeah. So got it. Got it. All right. See, some of you guys getting this? Yeah, I set up the numbers so they should come out to whole numbers. You guys. All right. Let's say show of hands who wins the race. So here's your options. Either Alan wins the race, Bob wins the race, or they still tie. So there's your three options. Show of hands. Who thinks that Alan in the lake wins the race? Who says Alan wins the race? Who says Bob in the river wins the race? Anybody for Bob in the river? Anybody think they still tie? Still tie. Ooh, I think most of you guys got it. Most of you guys said Alan wins the race in the lake. Yeah, you're right. Alan wins the race. Okay. Oh, in fact, I could have made these numbers anything. I could have made them paddle whatever as long as they paddle the same. As long as there's a river that's flowing, if you're in the river going with the river and then against the river, you'll always lose the race. Or the converse, if you pace yourself in a race, that's like Alan in the lake, you tend to win the race. Ooh, okay. Regardless of what these distances are or the river current speed. So let's do this. Can you guys say distance equals speed times time? Therefore, switch that around. Wouldn't time be distance divided by speed? So driving towards Jacksonville, I'm 180 miles away, going 60 miles an hour. It takes me 3 hours. Right, so let's say what's the time for Alan? He's going, let's do 2 ways for this. So 120 meters to the tree, 120 meters. He's going at 10 meters per second. He's paddling. Okay. Plus, he comes back 120 meters, also at 10 meters per second. Okay. Guys, how many seconds right here? Is that 12? Okay, and then 12 back, 12 and 12. Would that be 24 seconds? Okay. So it takes Alan 24 seconds. It's the time for Bob in the river. Oh, he's going 120 meters towards the tree. But, ooh, now here's where Newtonian relative motion kicks into play. Okay. Remember, Bob can paddle at 2 meters per second, but he's also getting a 2 meter per second boost from the river. So how fast is Bob actually paddling towards the tree or relative to the tree? Well, gives me 10 plus 2. 10 plus 2, let's call it 12 meters per second. Right? Plus, all right, then he turns around and immediately starts going back. Go back 120 meters the other way towards the start finish line. Ooh, but now that he's finding the current, how fast is he moving relative to the tree going upstream? 8. 8 meters per second, because 10 minus 2. He's fighting track. So go 8 meters per second. Let's see. Oh, guess how much time right here? What's 120 divided by 12? 10 seconds? Right. Ooh, I think he's winning the race at the halfway distance point. But coming back, guys, what's 120 divided by 8? 15 seconds. I think it's 15, right? 15? Okay. So put it all together, it's 25 seconds for the whole race for the two-way trip. Okay. Yeah. Which is more time than it took Alan to paddle the race. Yeah. So Bob loses, Alan wins. Again, you could make the river current any speed you want. You could make the distance to the tree and back any distance you want, and that'll always be the case. Okay. One way to think of it is even though there's a 50-50 split in terms of the distances they go, so you might say, well, wouldn't they just tie something? Right? The amount of time it doesn't work out, and the time is the variable that you want to focus on to see who wins the race. Right? So Bob is spending more time going slower, and when he was going faster relative to Alan, that was for a shorter amount of time. It's just a different way to think of it. Right? All right, so we got the relativity. Now hold on to this idea, because this is going to be important for the next few minutes. Right? You guys ready? Yeah. All right, so let's talk about light. Right? What is the speed of light, and how can people know this? Right? Now, way back in the day, hundreds of years ago, there was a Danish astronomer. His name was Ole Romer, and or I don't know if that's the correct pronunciation, but with that, right? He was looking at Jupiter. Here's Jupiter way out here, little red spot. Right? And Jupiter has some moons. One of the moons is called Io. He's watching Io go around, orbit Jupiter. Right? What he noticed is that from solar system mechanics, as Earth is sort of headed towards this Jupiter system, it looked like Io was going around a little bit more frequently, a little bit faster. As Earth was sort of headed away from Jupiter, say if like spring turns into summer or whatever, right? It looked like Io actually slowed down a little bit. Now, it's not because Io was actually changing its motion at all. Right? What he was actually picking up on was a little bit of a Doppler effect as applied to light. You guys remember the Doppler effect? Doppler? Stand by a sidewalk, car goes by, your pitch shift. That's just your perception, right? Well, light works similar to that. Now, the formula is a little bit different for light than it is for sound in terms of the Doppler effect. Right? But he did recognize that. And he said, hey, if I have a pretty good estimate of the distance from Earth to Jupiter, right, then I can have an estimate for the speed of light. Now, it wasn't super accurate, but it was about the right order of magnitude. I think he said it was like about 2 times 10 to the 8 meters per second. Nowadays, we know it's like 3 times 10 to the 8 meters per second. So it wasn't that far off, right? But what was it crazy accurate? Right? The first time that the speed of light was accurately calculated was in 1849. And this is a guy named Armand Fizeau. He was over in France, I think like right outside Paris. He did this experiment. And so this was back before the Civil War. We've known accurately the speed of light since 1849. Right? Here's how he did it. Right, you guys ready for this? Because later this week, I'm going to have you guys solve this puzzle. So if you're paying close attention right now, this will really help you out next couple of days. Okay? So he says, I'm going to have here a light source. I got a candle light source. Way off in the distance, many kilometers away. I'm going to have a mirror. You guys see this mirror? Maybe 5-10 kilometers away, something like that. Right? And I'll have, okay, here's an observer. So eyeball represent an observer. Right? And I'm going to have this cogwheel. So a bunch of teeth right here. Right? Now, if you just start off with the cogwheel not spinning, then here's what happens to the light. I'm following a single light ray. So some of those light rays might hit a tooth and just stop right there. Right? But some of those light rays go through the gaps in the teeth, hit this mirror way off in the distance, and come back to the same gap, and then this observer sees the reflection. So you can see the reflection of this light source in this mirror. Right? So that's not finding good, right? Right. Now, if light has a finite speed, it's crazy fast. It's something like a million times faster than the speed of light. Right? But as long as it's finite, then you can get this experiment to work. Where if you spin this cogwheel, and you have to spin this crazy fast for this to happen, right? That whatever light rays are running into the teeth, of course, never reach the mirror in the first place, same as before. Right? But whatever light rays pass through the gaps and then bounce off the mirror and come back, right? if in the time to go to the mirror and back, this might be like a few kilometers there and a few kilometers back, this entire cogwheel is turned just a few degrees so that each one of these teeth covers an adjacent gap, then what does this observer see? No. Nothing. Because the reflection is completely blocked. Right? In fact, the process building up the speed of the cogwheel, maybe you could change the singular velocity a little faster, a little faster, a little faster until you reach that effect. Here's what this would look like. So here's the reflection of the light in the mirror. Okay, so here's the observer sees this reflection of this light. Okay. Now, as you speed up the cogwheel, faster, it's going to look like a door is covering this light. And right when the door completely eclipses the light, then you know that you're spinning the cogwheel just at the exact speed so that this tooth covers an adjacent gap in the exact same time that it takes for the light to go that distance there and back. You guys got that? Okay. Now, what are the equations that you can associate with that story? Are you guys okay with that story? Okay, right. Now here's the equation to go with that. So we've got distance equals speed times time. Now the distance, this is a two-way distance. So whatever the distance to the mirror is, isn't it true you have to go there, but also back? So be 2 times the gap, right? So 2d, is that okay? Right. And the speed, well, we have a special speed. Let's call it the speed of light. So it's going to be c. You guys know in physics, lowercase c can be used for the speed of light, right? And that's what we're solving for. So that's our goal. I want to calculate what's the speed of light. That's going to be at the very end right here. Okay, fine. Let's see. Right. It takes some amount of time, maybe a tiny fraction of a second, right? For okay, distance equals speed times time. Right. So we got that. Right. Right. Now this cogwheel is rotating and it has to rotate so that one of these teeth covers an adjacent gap, and that's what this next box is for. So theta could be how far the cogwheel turns. I know a minute ago I said how many, like a small number of degrees, but really this should be in radians, right? And you guys tell me, if it made one complete trip all the way around, how many radians is that? 2 pi, right? So that's where I'm getting this 2 pi. So there's one revolution right there. But it doesn't have to turn even that far. It just turns just a little bit. How much? Well, it depends how many teeth. Now, guys, follow me on this. If suppose there was 50 teeth on this cogwheel, is this true that 50 teeth, there would also be 50 gaps between the teeth? And if the cogwheel has to turn so that each tooth covers an adjacent gap, does it only have to turn 1/100th of an entire revolution? Right? That's where this 2n is coming from. N represents the number of teeth. For every tooth, there's also a gap, hence a factor of 2. Okay? And the tooth just has to cover the gap. Right? Guess that? So we got this, check, right? Oh, you know what else I know that's going to tie these two equations together? Is distance equals speed times time, but for a turntable. You guys remember turntable physics? So here's how far this turns in radians. Here's how fast it's rotating, angular velocity, radians per second, and here's how much time. Okay? Okay? All right, now you can take these 3 green boxes, a giant system of equations, push these all together, and you can solve for c, which is the speed of light, and here's the answer right here. Okay, so it works out 2 times the gap distance times the number of teeth times the angular velocity in radians per second, divided by pi, right, if you do the math. Okay. Okay. Do you guys think you could probably solve that from scratch later this week? I'll probably give you, maybe all class period to do it. Okay, so see if you guys can figure this out, like Armand should go figure this out. Right. Anyway, he comes up with 3 times 10 to the 8 meters per second, which we know is accurate to this day. Right. So great, 1849, we got the speed of light. Right. So you guys ready for the next part of the story? Right, so speed of light, got that. Right. Now, the scientists are thinking, well, we know light has wave properties, so we'll call light a wave. We know it because we got this double slit experiment. We've got interference patterns from light. Right? And guys, think about this. How are you hearing me right now? Are the sound waves from my voice reaching your ears through the medium of air? Yeah, right? Because sound is a longitudinal wave. Sound is a pressure wave. And you need that medium. Right? Because if we were in the vacuum of space, would you be able to hear me? No, because sound needs a medium to travel through the vacuum of space, right? So scientists back in the 1800s, around this time, are thinking, well, that probably also applies to light somehow. They're just thinking, 19th century logic, right? Now, does the atmosphere extend from Earth all the way to the sun? Say, okay, well, probably not. So maybe light's not actually traveling through air necessarily as a medium, but it probably needs some kind of medium, they're thinking. Okay. So they call that medium luminiferous ether. Let me show you guys that spelled out. You guys see this right here? Luminiferous ether, or sometimes it's just called ether. Notice I put this in quotation marks. If you've never seen this term in a science book, that's probably a good thing, because this experiment I'm about to walk you guys through, they unintentionally disproved this idea. And I'll show you guys why. So they said, let's set out to discover what actually is the relative motion of this luminiferous ether? And here's why there logically would have to have been some relative motion. Let's have the sun right here, and maybe way in the foreground, we'll put the Earth. Right now, the Earth is already spinning on its own axis, so there's already some kind of motion. If you're on the equator, just by the Earth spinning, you're already going 1,000 miles an hour to the east. Okay? Okay. Then, if you also include the Earth revolving around the sun, right, that's an even greater type motion. Okay? And how does sunlight reach Earth? Well, if you're back in the 1800s, you probably thought, well, there must be some luminiferous ether medium so that these light waves can travel to us. Right? That was the thought. Right? Is that okay? Right? But no, this kind of reminds me of Bob and the River, doesn't it? Because if the Earth is spinning, is it true between night and day? The Earth is like the surface of the Earth is spinning opposite directions between night and day. Right? One way is that way, one way is the other, like in the linear sense, right? From the top, maybe it's always like counterclockwise. Right? And what about between season to season, the Earth revolving around the sun? Like in the summer, maybe it's moving in this direction. And in the winter, it's moving the exact opposite direction, isn't it? In terms of solar system mechanics, right? In the summer, it's going this way. In the winter, it's going this way. Winter, it's going around, right? So if there was some medium for light to travel on, then just like Bob and the River, like you would pick that up. Right? So let's go back to Armand Fizeau's experiment, trying to measure the speed of light. You say, well, if you measure the speed of light, say if you bounce a light ray going north-south, versus east-west. See, the north-south motion against the rotation of the Earth, well, the rotation of the Earth wouldn't really affect it. It'd be kind of like Allen in the lake. But east-west, well, that would be traveling with and then against Earth rotation, so that'd be like Bob and the River, wouldn't it? Okay. And also, of course, you have this revolving effect around the sun, and that should count for something too. Okay. So they were expecting that they could figure out what is the velocity of this luminiferous ether. Okay. And here's the experiment that's set up. We got a light source right here. I'm representing with a candle. We got some kind of detection equipment. I'm representing with an observer eyeball, but you guys get the idea. Right? We'll have a couple of mirrors that are equidistant. So whatever this distance is the same as this distance. And right smack in the middle of the whole field, we're going to put a beam splitter at 45 degrees. So this is a half silver mirror. What this would allow is whatever light hits it, half of it passes through and half of it gets reflected. You guys get that? Right, so it's half silvered mirror beam splitter. Okay. So let's follow a couple of rays of light. So got this ray of light, leaves this light source, hits this beam splitter, and half of it goes through, and half of it gets reflected at 90 degrees. Okay. Okay. Then bounces off these mirrors, okay, and then back towards the beam splitter. Some of this light goes straight through, and some of this light gets reflected also at 90 degrees and towards this detection equipment. Okay. Now, if guys, suppose this was oriented east-west and this is north-south, like a conventional map. If you're spinning with the Earth, isn't this line more like Bob and the River? Like you're going with the current and against the current, with the spin of the Earth against the spin of the Earth? And is it north-south being more like Allen and the lake, where if the Earth is spinning east and you're going north-south, that has nothing to do with the spin of the Earth? You guys got that? Right? Right. Also include the Earth going around the sun. That should be in effect too. Right? What they were thinking was this. They said, hypothetically, these two light rays should end up on this detector at different times. So they should be out of phase. Right? Out of phase, different times. Makes sense? Right? That's not what they got the first time they ran this experiment. They got the light rays were exactly in phase. They were hitting at exactly the same time. It says, okay, well, what a weird coincidence. That's okay. Let's just rotate this at a little bit different angle, or all the way up to 90 degrees if we want. Let's try this day versus night. Let's try the summer versus winter. And they kept doing this experiment, but over and over and over, right? Different conditions, different whatever. They didn't matter how they changed it. They always got the light was in phase. Okay. Now, of course, it's going the same distance. Both these paths are the same distance, right? But they were expecting different times, but they kept getting the same time. So the conclusion is inescapable that light's always traveling at the same speed, and therefore there is no luminiferous ether medium necessary for light to travel on. That's why last week, one of the questions I asked you guys was, what's the only form of heat transfer that can travel through the vacuum of space? And you guys said what? Radiation, right? As in electromagnetic light, right? Could be type of radiation, right? This is the experiment that led to that conclusion being understood to be true. Right? So light can travel through the vacuum of space. Okay, so we got this. A weird result. Nobody was expecting this, but this is what the science is showing. So got that locked out of place, 1887. Right? Now, Einstein comes along and he's looking at this experiment, some similar experiments, and he realizes that there's this conundrum set up. So not all is well with the universe. And Einstein's reasoning goes like this. Here, I'll just show you guys some notes from my last project right here. Guys, suppose we got this pickup truck, and we got Alan and Bob. And let's say the pickup truck can drive at 2 meters per second, and Bob can throw a baseball at 10 meters per second. You guys get that? Right. Now, if Bob can throw the baseball at 10 meters per second, and Bob measures the speed of the baseball, then the baseball is always going 10 meters per second relative to Bob, right? It doesn't matter which direction Bob throws the ball in, right? But what about Alan? Guys, Alan brought his radar gun. You guys see Alan with his radar gun, right? Now, if Bob throws the ball forward in the direction of the moving truck, then how fast does Alan's radar gun read the ball to be going? Huh? Guys, what is 10 meters per second plus 2 meters per second? Yeah, 12 meters per second, right? Or, guys, what if Bob throws the ball backwards? Then how fast will the radar gun read? Yeah, 8 meters per second, because 10 minus 2, right? Oh, kind of reminds me of like paddling in the river, right? We got this relative motion, right? Okay, so do you guys see for the baseball, we're just back to Newtonian mechanics all over again, right? But here's what Einstein realized is a consequence of this Michelson-Morley experiment. If you were to measure the speed of light in a moving vehicle, suppose Bob breaks out a Fizeau cogwheel and Alan breaks out a Fizeau cogwheel, and they both measure the speed of these headlight beams. You guys see this truck now has headlight beams? Send out speed of light 3 times 10 to the 8 meters per second. Okay. So Alan reads the speed of these headlight beams to be 3 times 10 to the 8 meters per second, speed of light. Bob measures the speed of these headlight beams to be 3 times 10 to the 8 meters per second, the speed of light. In fact, if they measured it down to the nanometer per second, they would get exactly the same speed of light. Well, hang on a minute. How is that even possible? Because if this truck is in motion, I know for the baseball, they were getting different readings on the radar guns. But if they bring out the Fizeau cogwheel and they're getting the exact same speeds of light, how is that possible? Einstein realized that the only way for this to be possible, actually, maybe I'll allow to you guys. I'll show you guys Einstein's experiment. Okay. Oh, by the way, here's some other equations he was looking at the time. It was Maxwell's equations for electromagnetism. There's different versions of these. Some of them have a c in there for speed of light. So there's this implication that was floating around at the time that there'd be some finite speed of light, regardless of motion. And people are trying to make sense of this. Einstein comes up with this thought experiment that involves a train. Now, you guys are going to get to see this twice today. Later on today, you'll see a rocket, which is probably more realistic, but Einstein liked trains, so we got a train model. Let's run the train. Okay? Let's have somebody inside the train and somebody outside the train. Inside the train car, outside the train car. Okay? And let's revisit a very important physics principle that you guys learned probably back in August. So it was one of the first things I ever told you guys. Okay? So suppose you are a passenger inside a car. Your friend's driving the car. You guys are driving north on 995. And you, the passenger, you're blindfolded. Can you distinguish the difference between going 50 miles an hour versus 60 miles an hour versus 70 miles an hour? Nope. You have no idea. What you can feel in the car is not velocities, but what? Accelerations. You can feel forces and accelerations. So if you speed up, slow down, or turn the steering wheel, you can feel that, but you cannot feel pure velocities, right? In fact, does this guy with the red hat inside the train car, does he even know if the train is moving or not? Right? Kind of like, hey, are we sitting on a spinning Earth right now, going almost 1,000 miles an hour towards the east? But can you feel that? Nope, can't feel it. Right? So this guy doesn't even know if the train car is moving or not. This guy with the green hat sees the train possibly in motion. Let's have the train in motion. Okay? Now, let's throw a light source on the ground, maybe represented with a flashlight here. Let's throw a mirror on the ceiling. So a single light ray from the point of view of somebody inside the train car, this guy with the red hat, looks like the light beam goes straight up, bounces off this mirror off the ceiling, and straight back down. So straight up, straight down. That's okay, right? Straight up, straight down. To this guy outside the train car with the green hat, he sees the light beam do something different. He sees light ray go on a diagonal path, bounce off the mirror on top, and then come back down. So it travels a further distance. You guys get it? Right? But both of these guys perceive the exact same speed of light, which again runs into a conundrum. They both break out a Fizeau cogwheel. They both get exactly the same speed of light. Because if this train is in motion, it's also moving some distance. We'll call it VT. So V could be the speed of the train, right? Right. C is the speed of light. V is the speed of the train, right? Right. If both of these guys perceive the exact same speed of light, but different distances. Remember, the guy inside the car says it just goes up and down. The guy outside the car says it moves on a diagonal path. The only way to reconcile that difference is if those two guys perceive different what? Time. Different time. Different time. All right, yeah, you figured out what Einstein figured out. Yeah, different time. So you can solve this with the Pythagorean theorem, and that's what this green box is right here. It's just Pythagorean theorem. Right? Let's break this problem in half. Let's just have light ray go to the mirror, and then we'll stop it right there. Right? So do you guys see a nice right triangle right here? Nice right triangle. Right? So we got 3 legs of a right triangle. So the distance that travels straight up, according to the guy with the red hat, is just speed of light times. I'll call this T naught. So T naught is going to refer to the time inside the train car. Right? This guy outside with the green hat sees it travel along the diagonal distance, which is CT. Now, even though it's the same speed, it'd be a different time. I'll just call it plain T without a subscript. So that'll be the guy outside the train. Right? And then this other leg of the triangle is the distance the train car moves. We'll call it VT, right? Speed times time for the train. Right? And you can set up a Pythagorean theorem with to have a relationship between those distances. Okay. Now, once you have that relationship, can you apply some algebra and rearrange this and solve for one guy's time in terms of the other guy's time? Okay. This ends up being the end result, and I want you guys to see that that is true. Okay, just come up with that. Okay, so here's the full proof. You guys see that first line is that Pythagorean theorem setup, right? Now, I will of course post this video to Google Cloudkin later. So if you really want to check my math, then please do. Right? But line. Here's the end result all the way at the very bottom. This says this. It says the guy outside the train, his time is equal to the guy inside the train's time divided by, and then you guys see in brackets is a square root. Is that square root factor is called the Lorentz factor. So it's the square root of 1 minus v squared over c squared, where v is the speed of the train, c is the speed of light. Okay, is it? And so yeah, so they do perceive different times. This is called time dilation. Time dilation. Okay. And well, whose time would be faster? Okay, let's run this equation. Suppose the guy with the red hat has 1 unit of time. Let's call it, I don't know, 1 hour. Let's call it 1 hour, right? And you divide by the square root. Now, the speed of the train can be anywhere between 0 and c, right? So maybe we'll call this a relativistic speed, maybe like half the speed of light or something, right? Guys, v squared over c squared, this fraction itself is always going to be bounded between what and what? Okay, so if v, the speed of the train, would be like half the speed of light, wouldn't half the speed of light divided by the speed of light be a factor of a half? Is that true? Right? Which is always between 0 and 1. And then if you square that, isn't it also between 0 and 1? Because what's 1 minus anything between 0 and 1? It's still between 0 and 1, right? Because 1 minus a half would be a half, 1 minus a quarter is 3/4, so on, right? And the square root of anything between 0 and 1, you can try it. It's stuck between 0 and 1. Okay. Now finally, we're down to the last step here. Okay. If you take 1 hour and you divide by, say, 0.5, is that going to be less than an hour or more than an hour? More than, because 1 divided by 0.5 would be like 2, right? Right. So 1 hour inside the train might correspond to 2 hours outside the train. Okay. Now, that exact ratio depends on how fast you're going, but it's always going to be more time outside than inside. And I try to make the clock faces also align that. You see more time passing on the green clock and less time passing on the red clock. Is that just trying to show that too, right? Right. So how important is this effect? How subtle is it? Does this matter? No, this is a really subtle effect. It is measurable with atomic clocks, not necessarily with a quartz watch, right? But maybe with atomic clocks, right? It does matter to certain technologies. You guys have GPS on your phone, use that to navigate around town. Okay. GPS would not work if you did not account for relativity. Or if we did get it to work, it'd just be like trial and error. We wouldn't know why it worked if we never come up with this theory, right? So how about this? What if the speed of the guy with the red hat is relatively slow compared to the speed of the guy with the green hat, which has always been true for human motion. The fastest any human has ever moved relative to any other human, I imagine it's probably like in a rocket in space, maybe like orbiting the Earth or something kind of like that, right? And even that speed is so tiny compared to the speed of light that this fraction right here, b squared over c squared, is fairly close to zero. Not exactly zero, but fairly close to zero. And that's definitely true whenever you're in the interstate, in your car on the interstate. 70 miles an hour compared to the speed of light is almost nothing. So let's do that. Guys, if v is very, very tiny compared to c, then what is this fraction equal to? That'd be 0. What's 1 minus 0? 1. What's the square root of 1? 1. What is anything divided by 1? What would be itself, right? And what I'd be saying there is, as long as you're moving at a non-relativistic speed, right, like interstate highway would be almost nothing compared to speed of light, then they would agree on how much time has passed, right? That's why if you like drive to Merritt Island and back, that you don't really perceive a time dilation. You never would be able to with your brain. Even astronauts that are in the International Space Station for months at a time, the amount of time dilation they get is on the order of magnitude of like milliseconds, right? So you could almost say you could throw it out. Like, how would that even matter, right? Again, but I'll show you guys next few days. GPS, it definitely does matter. Right. All right. So you guys good with that so far? Actually, you know what? Probably a good time for a demo here. Let me break out my videos. Video. All right, we'll come back in. More posters later.
Once upon a time, there was a pair of identical twins, except they were not so identical. One enjoyed the settled life on Earth, while the other was more wild and adventure-seeking. One day, the wilder one decided to embark on a journey into deep space. The two embraced before parting. The rocket traveled at near the speed of light straight into the uncharted dark depths of space. It took him 5 years to realize how much he missed his twin brother. He turned around and headed straight home. Another 5 years passed before he returned at last to Earth. Upon landing, he ran to reunite with his long-separated twin brother, only to find him no longer his twin, but an old man. During his 10-year journey, 50 years have passed on Earth. He finally discovered what he truly valued more than adventures. The end.
Wait a sec.
What?
Go back. Way back to the beginning.
Okay.
Like, I thought they were the same age at the beginning. How did they end up being so different in age?
That would be an effect of time dilation. Not in that way, at least. So let's imagine a train traveling really, really fast, and our explorer hops on while our settler remains behind. Now imagine that there's a light bulb fixed onto the train cart. As seen by the explorer, in order for the light to go from the light bulb and back, it only has to travel up and down.
All right.
But the case for the settler when he's looking at the train is different. In order for light to return to the light bulb, the settler sees it traveling diagonally with the train.
Oh, that's like when you're in a car and you're throwing a ball upwards. The ball returns to your hand because it only goes up and down. But to someone on the street, the ball actually has to travel with the car to return to the passenger's hand. So the ball actually travels farther than it appears to the passenger.
Yep. But there's no time dilation because the speeds of the ball are different. If the car's not moving, the ball only goes up and down. If the car is moving, however, the ball also travels forward with the car. So it is essentially thrown diagonally upwards. The forward motion added to the up and down makes it travel faster, covering the farther distance in the same time interval. Light, however, is different. No matter what frame of reference you're in, light travels at the same speed. C, the speed of light.
No duh, light travels at the speed of light.
Anyway, going back to the train, the two observers see the light tracing out different paths. The explorer sees the light travel a distance, and the settler sees the same light travel a farther distance. Since light travels at the same speed, it would take longer for it to cover the distance the settler sees. So the same phenomenon to the settler would take longer time to happen than it would to the explorer, and so time on the train would appear to dilate.
But doesn't the same light argument apply to the passenger in the car? Like, if you put a light bulb in the car.
That's true. But in comparison to the speed of the car, light is so fast it is almost instantaneous. So technically, time in the car is dilated, but the change is hardly perceivable.
Oh, So if time is dilated, as long as the frame is moving in respect to another frame, then can't you say that time is dilated for the cellular in the explorer's frame?
Here's the problem. A moving frame is not enough. You need an inertial frame, which is a frame that travels at a constant velocity. For an accelerating frame, which does not travel at constant velocity, time dilation will not happen.
That would be when the explorer stops and turns around to go home. He has undergone acceleration.
Yep. You can also argue that the Earth undergoes acceleration as seen by the explorer on the rocket, but only the rocket physically experiences acceleration, so you cannot argue the other way around.
I thought everything in relativity is relative to each other.
All right. So it's called twin paradox. If you guys ever hear your twin paradox, that's the story they're talking about. That's pretty good, right? That's pretty good. No, something to keep in mind is that as long as you're along for the ride, suppose this was like rocket twin. Well, maybe I should call this guy rocket twin from now on. Right? If you never notice anything weird about your own clock, right? And then Earth twin never noticed anything about his clock, right? So Earth twin says my clock always beats at 1 second per second, and rocket twin says my clock always beats 1 second per second. Now, if there's some window in the rocket and they have telescopes and they're looking at each other's clocks, okay, that's where they see something weird. So that's where rocket twin looks at Earth twin's clock and it looks like it's going, and then Earth twin looks back at rocket twin's clock through the window, and it looks like it's going tick tock, tick tock. Maybe he's going like almost the speed of light, right? Or something like that, right? So you get the paradox, right? Now, if there's this time dilation, you sit around and think about it a little bit. There have to be some other type dilations too, or contractions, right? I'll show you guys why. Suppose you're here on Earth. There could be Earth, right? And way off in the distance is like some other planet system. Right? Let's say it's like 10 light years away. So from Earth to this other planet. Right? So I'll say X for a distance could be like 10 light years. Right? You guys know light years is a distance, the distance light travels in the air. Right? So if you hop in a rocket, right, let's have rocket twin right here. Gotta head towards this distant star system. Right? Let's say at a relativistic speed. So I'll say v equals, I don't know, like half the speed of light or something like that. Right? Call it a relativistic speed. So you get these time dilation effects. Right? Then the fact that Earth twin here and rocket twin here perceive different amounts of time passing, right? You don't get each other's clocks through the telescopes and realizing they're ticking at weird rates, right? Then, Earth twin is going to see rocket twin take probably about 20 years to reach this planetary system, because half the speed of light, 10 light years, shouldn't take about 20 years to get there, right? But remember, from rocket twin's point of view, it doesn't take that long. I think if you run the numbers, it's something like 80 or 90% of that, right? Okay, so it's a little shorter time. But if it takes a shorter time, what that ultimately means is that rocket twin does not perceive this distance to be the full 10 light years. It's more like 8 or 9 light years. Again, if you like run the numbers depending on different speeds, right? So what I'm trying to get at is that it's not just time that dilates. There's also a length contraction, and for that matter, there's also a momentum dilation that comes out of this too, right? So it could work like this, right? So you've got rocket twin, Earth twin, right? Here's time dilation, right? Here's the corresponding length contraction, okay? And here's, momentum dilation, right? These formulas all look pretty similar, right? They all got the Lorentz formula, Lorentz factor in it, right? That's the square root, this Lorentz factor. So, right? Now, this momentum dilation is something that particle physicists over at CERN, the Large Hadron Collider, see all the time, right? Now, I put in a little bit of hydrogen, like however many grams, right? They'll speed that up in this giant synchrotron close to the speed of light. It's like 99.9 something percent the speed of light. And as they do, they're steering it with magnets. It looks like there's more and more and more mass and momentum than there should have been where they put it in the start book. Right? And that's an effect of special relativity. So that's another place you see this. Right? Ooh, show you guys a graph. Like you can make graphs out of all these equations too. So here's one of the graphs. If you did a time dilation, it would look the same shape. Right? So here's momentum as a function of speed. Right? Now, how does Einstein physics map onto Newtonian physics? Because if you're going on a non-relativistic speed, like less than 10% of the speed of light, it's pretty much a match, right? So you speed up to Earth orbit speed, right? That would be basically not relativistic. So physics just mostly boils back down to Newtonian mechanics, right? Again, there's a couple of exceptions, like GPS, you need to consider Einstein, right? So, but as you approach the speed of light, these two different physics diverge more and more. Now, didn't Newton say momentum is equal to mass times velocity? You guys remember that last semester? You guys remember collision car expand? mass times velocity is momentum, right? Einstein says, well, it starts out being true at slow speeds, but as you approach the speed of light, then you have to divide by the Lorentz factor. In fact, you reach a, do you guys see a vertical asymptote here? I want you guys to see why this is a vertical asymptote. Because what happens if you plug in C for V? So what if you did reach the speed of light? Because what is C squared divided by C squared? Is that 1? What's 1 minus 1? 0? What's the square root of 0? 0? What is anything divided by 0? And don't say 0. Undefined. Undefined. Okay, that's this vertical asymptote. And since that's also true for time, right? Like this time right here, this time right here, right? You could never reach the speed of light. And if you did approach the speed of light, then you would watch the rest of the universe. You would watch it like speed towards its death, right? You would watch like a billion years pass into you. What would be like a second, something like that. Right. Also, there's an interesting consequence from this, which is that from the point of view that of anything that is moving the speed of light, say like photons, you could make an argument, especially from this length contraction, that space does not even exist from the point of view of photons, which is a weird thing to think that, but that's an interesting thought. Right? Yeah, let's do this one real fast. And then I got one more video for you guys after this. So Minkowski space-time diagram. There's a 2D looking version of this. I try to make this one fancier, but normally have a space axis and kind of a time axis. Okay? I gave you guys 2 space axes on this one, so x and y could be spatial dimensions. Okay, and in place of the time axis, it's really common to do speed of light times time to sort of make it also a distance axis, right? But you can think of it like time is ticking forward, like going up this axis system, right? So here's the past and here's the future. You guys that? Okay. Now, there's only a certain amount of the universe that you can ever interact with that could either affect you or that you can affect. Like if some event happens on Mars like 2 seconds ago, we're not going to know for several minutes because it takes light and information and any effect from Mars to affect us. It takes several minutes for that to reach us. Right? If Mars turns blue, we won't know for like several minutes. Right? Right. So that'd be like something out here. Right? Now you and me and all of us, we're all like at the center of the system. Right? Anything that can affect us can only reach us at the speed of light. So that would put it in this cone. Anything outside this cone, there's no way it could ever affect us. Right? Going into the future, anything that you could ever affect. Right? You send out an email or send out a radio wave and send it through space. Right? It can never reach like this point here. Right? Like you can't send an email to Mars in 2 seconds, right? Because it takes several months. Right? So it's going to be inside this cone. Right? And these red dashed lines I put going at the speed of light. So photons are always traveling at the speed of light. So that'd be C, right? So if this vertical axis is CT, that would make this angle a 45-degree angle. All right. So there you go. Here's Minkowski. So last one I got for you guys. Let's do a light contraction here.
So I'm going to talk about gamma.
I'm going to skip the first couple minutes of this. He talks about gamma, the Lorentz factor. He goes through a few examples of this. Like there's a particle example. There's like cosmic rays coming in from the sun. I'm going to start it right here. All right, you guys ready for this train? This one's crazy.
In a tunnel. The idea is you've got a train and you've got a tunnel which is exactly the same length as the train. And so if you're a plane spotter who's standing there beside the railway watching the trains go by, you see this train approaching, and because this train's moving relative to you, you see it Lorentz contracted. It's a bit shorter than it should be. And that means that as it goes into the tunnel, it disappears completely in the tunnel because it's shorter than the tunnel. Like the tunnel's not moving relative to you, you're standing next to it, so therefore the tunnel is its normal length. But because this train is moving relative to you, it becomes a little bit shorter, so it disappears into the tunnel. Fine, so it actually is briefly kind of hidden at both ends of the tunnel. But now if we think about somebody sitting on the train's perspective, somebody sitting on the train, they think they're stationary, the table there in front of them, they can drink their cup of coffee. When they put it down, it just stays there. So they're in their reference frame and everything's normal. And they're seeing the countryside rushing by. And so they see this tunnel approaching them at high speed. And of course, because they're seeing this tunnel moving, the tunnel should be contracted. And so from their perspective, they should never completely disappear into the tunnel because they see a tunnel which is shorter than the train. So therefore, the train never completely disappears. By the time the back end of the train's disappeared into the tunnel, the front end's come out the other end. And that's all well and good. And okay, maybe they just agree to differ about whether the train is shorter than the tunnel or not. But unfortunately, you can then do another experiment, which is you can say, okay, so if this train spotter actually is, has a rather a lot of power, and bizarrely, someone has installed 2 large guillotines, one at either end of the tunnel. And at the moment the train disappears into the tunnel, he pulls a lever, which briefly makes these guillotines come down and then go back up again. then from his perspective, that's fine because the train's disappeared into the tunnel. They can do that without doing any damage. Okay, from the point of view of somebody approaching the tunnel, if this happens, it's not going to be such good news because from their perspective, the train's longer than the tunnel, which means either the front of the train gets chopped off or the back of the train gets chopped off or both. Okay, and this is something that everyone has to agree on, right? Because if you actually do the experiment, either you end up with a smashed train or you don't. And ultimately, that's going to be something that everyone has to agree about. It's not something that you can just say, well, that's just a matter of perspective. That's all just relative, right? Either the train gets broken or it doesn't.
So what happens?
So there is a resolution to this paradox, and the resolution to this paradox turns out to be something very fundamental in relativity, and it's called the relativity of simultaneity, which basically means which things which are simultaneous in one reference frame are not necessarily simultaneous in another reference frame. So in fact, both of these people agree that the train doesn't get smashed, but the reason why they agree the train doesn't get smashed is different, right? The guy who's pulling the lever says, well, the train obviously didn't get smashed because it was shorter than the tunnel, so that was fine. The guy in the train sees something completely different in that what he says is that actually what happened is the train was approaching. Before it went right through the tunnel, the front guillotine came down and went back up again. Then after it had pretty much passed through, the back guillotine came down and back up again. And so actually they kind of missed the train as it went through. And so this is what both of them see. They both agree that actually the train's fine. But the reason is that because the things which were simultaneous in one reference frame, the guy who was just standing next to the tunnel said these things happened both at the same time. The guy who's in the train said actually no, one happened first, then the other. And so that's the resolution to the paradox, is that this whole concept of simultaneity kind of goes away in special relativity. That things which one person says both these things happened at the same time, somebody else will say no, actually that one happened first and that one happened second. Because whether things happen at the same time really depends on what reference frame you're measuring them in.
But what's the fact? Did the train disappear in the tunnel or did it fall out the ends? What actually happened?
Both. It just depends on whose reference frame you're in, right? In one reference frame, that's exactly what happens. If you think about it, the train sticking out of both ends of the tunnel relies on somebody's simultaneous measurements, right? The front was sticking out at the same time that the back was sticking out. And because different people disagree about simultaneity, it's quite possible for them to disagree about whether both ends of the train are sticking out of the tunnel at the same time.
How does this go down when you teach this to students?
The students love it, I have to say. I mean, one of the really nice things is, although we avoid all the maths in these videos, actually the maths you need to do this properly isn't very hard. The most difficult maths you need to do this properly is trigonometry and just basically Pythagoras' theorem. The square on the hypotenuse is equal to the sum of the squares on the other two sides.
All right. There you go. Relativity of simultaneity. There's a pause point. Guys, have a good night.